Hello everyone, it's my pleasure to give you a presentation here. My name is Jingqi Chen from Beijing Institute of Technology. Today I would like to introduce a semantic modeling approach supporting property verification based on Satisfiability module series. Here is my content. And the first part is introduction. MBSE provides a solution to support complex system development through the concept, design, analysis, and verification using models across the entire life. And property verification in MBSE formalizes and evaluates the constraints consisting of model elements for checking whether the system models remain valid. Property verification can be applied in the architecture trade-off efficiently too. When the alternatives with different properties exist, the property verification is able to evaluate properties of each probable alternative. So there are some advantages of using property verification for trade-off problems. Using property verification in MBSE can visualize all alternative architectures in a simple way, and the trade-off optimization is from global view instead of simulating all probable alternatives one by one. However, challenges exist. As a unified method to execute property verification for trade-off optimization in MBSE applied in multi-domain modeling languages is lacking. Also, there is a lack of the method of unifying the information interaction between the models and the trade-off process. And the existing methods involve multi-adding tools or modeling languages, which is unfavorable for the usage of property verification. So, our goal is to propose a property verification approach based on a unified modeling method and define the corresponding syntax and semantics of property verification based on the multi-architecture language comma and Satisfiability module series. The next part is our related works. The definition of property verification is clear here. Property verification belongs to the formal verification and formalizes and evaluates the constraints of formal models. The Dr. Gogler, Dr. Brucker, and Dr. Pires combine the UML and OCL to formulate constraints and check the characteristics. And Dr. Kolovos abstract the syntax and the semantics of OCL to construct its own property language for testing the consistency of model transformation. But there are still some limitations here. Firstly, most research on property verification are developed based on one modeling language. So, that is difficult to reuse the same method for other specific languages, and the languages of using property verification and modeling are separated. So the languages of property verification involves many languages and solvers, which are not conducive to users' understanding and learning. So we need a new approach for property verification in a unified way applied in multi-languages. And the third part is show how the proposed method works from the four parts. Firstly, we state the problem of trade-off. The trade-off is a decision-making process to evaluate the characteristics of each system in order to find the optimal solution. The execution process begins with modeling and the trade-off problem, including the space A of alternatives. When the models are finished, the property verification is applied to formalize the model elements corresponding to the requirements and the system architectures into the constraints C and optimizing targets O and evaluates the alternatives according to the constraints and the optimizing targets and finds the optimal one. Second is a theoretical basis. GOPPRR modeling method is a modeling basis. The GOPPRR modeling method is the most powerfully expressive mathematical modeling method because GOPPRR supports the most first-class modeling concepts and the most relation patterns. Karma language is based on GOPPRR modeling method, which supports modeling in multi-languages. The GOPPRR modeling method includes 6 mathematical models: graph, object, property, point, and relationship, role, extension. The mathematical models are indexed to the metamodels, and metamodels are combined to the instances. The next basis is Satisfiability module series. Although Karma, based on the GOPPRR modeling method, is able to formalize modeling alternatives, but it cannot quantify and evaluate the alternatives. In order to support the description of property constraints and the implementation of property verification in MBSE, Satisfiability module series is used as a theoretical basis to formalize the property instances to be constraints in first-order logical expression and evaluate them. SMT is consisting of a series of axioms based on first-order logical expression, including multi-mathematical series. Moreover, SMT can not only provide the theoretical basis for checking the satisfiability of the first-order logical constraints, but also has corresponding solvers, so it can implement the verification in a unified theory. Based on the theoretical basis, all kinds of alternatives can be extracted into the constraints consisting of model elements. Each alternative is consisting of different property instance sets, which are from the M1, the model level. And property instance set includes all possible property instances with different values in the formalization. The subscript other type refers to the type of the 5 mathematical models, and the superscript protype refers to the type of property instance such as string, real, integer. And when the property verification bases are constructed, the constraints can be constructed by the captured property instance of the models and other elements which has return value of Boolean through the mathematical operators of SMT. And C refers to the unified description of constraints with property instance. R is a set of real number, and dot refers to an operation process based on SMT that supports the mathematical operation based on SMT, including the Boolean operators, arithmetic operators, array operators, and compression operators, or some adding operators. And the optimizing target O is the same, which combines the numeric the operators and the optimization operators is formalized based on SMT. O is the objective that maximizes or minimizes the arithmetic expression, where the symbol M refers to the optimization operator set, including the minimization operator and the maximization operator. And by the way, the constraints and objectives are combined by the AND operator. So, when the basics are defined, this is abstract grammar supporting property verification based on Karma. It includes 7 parts: the block declaration, SMT analysis, the statements of getting models, and the general solver declarement, and the statements named solve, declare, and solve statements, and optimize statements, and the variable declaration. Compared to the general solver, the optimized solver can add statements of minimizing or maximizing. So the method of semantic approach supporting property verification is following. First, various models according to the design requirements are constructed in the modeling perspective of metagraph based on the GeoPPRR modeling method. The metagraph is a tool based on the Karma. And the second, engineers make use of the Karma language to formally describe the constraints of property instances and optimization targets according to their purpose. The third is the metagraph compiles the Karma language constructs and traverse the generated abstract syntax tree to execute the corresponding SMT solver to verify whether the constraints are satisfied. And the fourth is the result, including whether the constraints are satisfied, and the optimal solution that meets the given constraints automatically return to the result perspective, which are displayed to the engineers. And the next one is case study. The case study is optimizing the matching problems between workers and their working process. There exists the assembly line with 7 processes, whose processing priority is shown, and 3 workers are required to complete these 7 processes. Constraints and objectives are follows. There are 3 constraints and 2 objectives. The first graph is requirement diagram. It describes the requirements for optimizing the matching relationships between workers and processes. The use case diagram figure 2 involved in the process of production are described. After receiving the order from the customer, the production management formulates the production plan to arrange workers to produce on the assembly line in order, and the processed products are delivered to the customer after meeting the requirements of ordered quantity. Figure 3 is an activity diagram which describes the process sequence and corresponding processing time of the assembly line. Figure 4 use case diagram illustrates the alternatives which need to be determined as defined above. So, if the models in CSML about matching problem are finished, the property instance which need to determine is the relationship between each process and each worker. The value of such property instance can be 0, which means the workers does not execute the process, or 1, which means the worker executes the process. The property instance set is consisting of the property instance with 1 and the property instance with 0 for different connections between workers and processes. The Karma script of property verification is following. Firstly, a 0-1 matrix X consisting of property instances is defined whose rows refers to the processes and columns refers to the workers. And the first constraint is each process must be implemented. The second constraint is the processing priority. The third constraint is each worker must carry out 1 process at least. Then, the optimizing target O is defined. The multi-objective is defined. The multi-objective is the sum of processing time of first worker and balance delay time, which refers to the efficiency. First, stand time of each process is captured from the model, then calculate the time for each worker and construct the objective. The result comes to the front end in the form of table. Like this is a table, and after 983 milliseconds, worker 1 carries out the process 3, and worker 2 carries out the process 1 to 4, and worker 3 carries out the process 5, 6, 7. The balance delay time is 58 seconds, and the production efficiency is a 3%. And working time is first worker is 57 seconds. Next is the conclusion. So, the proposed property verification based on GOPPRE modeling method and SMT is applied and verified to formalize the property instances and operate the property instance as a first-order logical constraint to be evaluated, and comma with the extended syntax and semantics based on SMT is used to be the unified language of modeling, formalization, operating, and property instances and evaluation. Through the case study, the effectiveness of the proposed approach is validated. Our future work will focus on the optimization solver, because the optimization solver does not perform well in supporting non-linear optimization, and the trade-off optimization focuses on the alternatives with different property instance only, without other model elements. That will be our future work. Thank you for your listening. This is my presentation.